Cool. All right. Well, welcome everyone. As you guys probably noticed, this recording is going to be a little bit different. It is not live in lecture because I forgot to record our live recording, but I do want you guys to have access to this when you are studying for the final exam. So I'm going to go ahead and simply re-record this lecture from my computer. So I'm going to go ahead and get started. I will try to point out areas where students ask questions, but again, like it's not live, so it might not be. If you do have any questions, like please feel free to comment on the presentation slide. Like I think there's a few students already that left some notes. So definitely like comment on there. I'm happy to come through and answer them. Ask on Piazza. I'm happy to come through and answer that. So let's get started again for lecture today. Homework 8 is due on Monday at 11:59 p.m. I will be having a homework party on Monday right after lecture. So if you want to come hang out with me and work on your homework, that is fantastic. The other thing to keep in mind is I did upload a homework 8 walkthrough to YouTube, so this should be available for you. The intention of these walkthroughs is to try to answer any possible questions that come up with the homework. This one's about an hour and a half, and it does go through both the coding and the written part of the assignment. So what I really encourage you guys to do is try the assignment on your own, see if you can get fairly far with it. If you're struggling, if you're having a lot of trouble, and for some reason you can't reach me, or Piazza is not working for you, feel free to use the walkthrough as an additional resource. Like I mentioned, homework 8 party on Monday. And finally, we also have a Linux coding challenge. So please click the link RSVP. This is going to be hosted by Meta on April 21st from 3 to 5 p.m. It's going to consist of 4 problems, and you're going to get to, you're going to be introduced to the production engineering role at Meta, which is a really good mixture of sort of like systems and software. Right. Another announcement. So my wife and I actually, or my wife, I did not. So my wife launched her new feature on Google Lens. It's called multi-search. So if you're interested about it, please just search it on Google News. It's called multi-search. You'll learn all about it. There were several news articles written. And if you want to try it out, you can use it directly from your phone, whether it's iPhone or Android. All right, so let's get started. Today we're going to be covering scheduling. We're the scheduling problem, and we're going to be using a greedy algorithm to solve that. And then we're also going to jump into Huffman coding. So let's get started. The first thing to keep in mind is we are going to wrap up what we did last Friday, which was the problem of activity selection. So just to remind you guys, the activity selection problem, essentially, you have a set of activities that you're trying to do. All the activities have a particular start and finish time. So the start and finish times are given to you. You are not able to choose the start and finish times. But what you can choose is you can choose which activities you want to do. So last time we ended by figuring out that there was a greedy algorithm to do this, where we select the earliest ending time first. So this does work. Last lecture, we talked through several other options that do not work. And this one does. So today we're going to go through how you would go proving that this approach is a reasonable one and one that will give you the optimal solution, where the optimal solution is maximizing the number of activities that you perform. So to get started, let's actually see how the algorithm works. So the way the algorithm works is you pick the activity that you can add with the smallest finish time. So implementation-wise, if you were, let's see if I can annotate. If you tried to implement this, what you would do is you would be given an array of start times and an array of finish times. And the very first thing you want to do is you want to sort the finish times. So you want to be able to move along and hit activities based on their finish time. So the very first activity you would look at here would be A2, then you would look at A1, then you would look at A5, then you would look at A4, then A3, then A6, then A7. And the order in which you look at them is you're always looking at the one that finishes earlier that you haven't looked at yet. And essentially what we do is we look at the very first activity. And what we're going to do is we're going to look at the activity, and we're also going to keep track of the end time of our previous activity. So at the very beginning, that is going to start out here. So it's going to be this line that starts at 0 because we have no activities, right? And what we do is we look at the first activity based on its ending time. And then we say, well, what's your start time? What's the start time of this activity? Okay, so if the start time is greater than our previous ending time, then we take this activity because that means that we can do this activity. It's not overlapping with anything else. Once we take that activity, we update the ending time. So now this ending time gets updated to the activity we have now selected, right? So now we select activity A2. So we add it to our list of activities that we've selected. We update our ending time to be the ending time of A2, and then we continue. So the next activity we look at is going to be A1. Now A1, we're going to look at its start time, and we're going to notice that its start time is before our ending time. So we can no longer do activity 2. It is not an activity that we can do. So we don't take it, we continue, and now we look at A5. So looking at A5, we notice that its ending time is the next smallest ending time. So that's why we went to A5 next. We look at its start time. So we go over here to look at what is the start time of A5. And we notice that the start time is after, right, our previous ending time. So we go ahead and update our previous ending time to the new ending time. So now our ending time is here at the end of A5. And we go ahead and pick A5 as an activity that we want to do. And then we continue. We move on to A4. A4 is not eligible because, again, its start time is going to be before our current ending time. So we can't do that activity. Then we move to A3. We can do A3. And again, our current ending time gets updated to here. We cannot do A6, but we can do A7. And as you'll notice, this gives us a total set of 4 activities. And the claim is that these 4, they're at most, you can ever do 4 activities. So no matter what you do, you can only do 4 activities total at most. Now, this may not be the only way you can do 4 activities, right? In this scenario, you can actually, you can see pretty clearly that you could do A1, A4, A3, and A7. This is also an optimal solution where you have 4 activities, right? But the one our algorithm picked is also 4, and the claim is that an algorithm will always pick an optimal solution. So there may be several optimal solutions, but our algorithm will pick one of them. Okay? So if you understand that, then you've basically got the gist of how the greedy algorithm works. So moving on to the next part, I'll just skip this because it's just highlighting what we would do. The running time of this algorithm, obviously, it's pretty fast. So if everything's already sorted, it'll be O of n, because we iterate through the activities using their finish time. And then for each activity, we look up its start time. So that can be done with a hash map or even with an array. It's relatively easy. If it's not sorted, then you have to sort them first. So it's going to be n log n. Now, what makes this algorithm greedy is that at each step of the algorithm, we make a choice. Hey, I can increase my activity by 1. I can do this one more activity, and I can leave lots of room for future choices. So let's do that and hope that this is a good activity to pick. The hope part is the part that makes it really greedy, right? Because you're hoping that at the end of the day, this results in a globally optimal solution. So you're not looking at all the activities in the future. You're not looking at the activities you already did. You're only looking at the next possible activity, and you're picking the one that finishes the earliest. So the intuition is I'm trying to pick the next activity that leaves the most room still open after I do it. And it turns out that that will give you the most activities you can do in a day, right? So these are the questions you want to ask yourself. Does this greedy algorithm work? The answer is yes, it does work. And we're going to go through like an explanation as to why it works. And yeah, so the answer is yes, it does work. In general, when are greedy algorithms a good idea? When a problem exists that is nice optimal substructure. So this problem does have a nice optimal substructure, which is that you can focus on the future activities. The greedy approach is often the first you think of, actually. So when you look at a problem, usually it's not hard to think of greedy solutions. The issue is that it's hard to show that greedy solutions actually work in every single case. Okay. So for this one, we have why does it work? We want to figure out why it works. And the general idea for most greedy algorithms, when you want to prove why they work, is you want to show that the choice your algorithm makes does not rule out an optimal solution. Like, in a sense, you want to make sure that the solution you have built so far is part of an optimal solution, of some optimal solution, right? There may be many optimal solutions, but you want to make sure that every time you add a new activity to the current set of activities, though that activity exists in some optimal solution. That way, at the end of the algorithm, when you've added all the activities, by definition, that solution must be optimal. So the way we're going to think about that is we're going to look at this activity A1 here. And our next choice that our greedy algorithm would do is it would pick activity A5. And again, if we go back to our greedy algorithm, you'll notice that the reason it picks A5 is because it's the next activity with the earliest ending time that does not conflict with what we already have, A1, right? So if A5 is in the optimal solution, so let's suppose that the optimal solution is A1, A5, A3, A7. That is, you can do 4 activities. This is the optimal solution. If A5 is in that optimal solution, then we're done, right? Our algorithm did not rule out an optimal solution because it included A5, which we know is part of our optimal solution. So that's fine. Now, the other problem is suppose that we are trying to choose. So now I'm going to change the AK here just to make it more general. So we're at the ith step. We're considering choosing the next one. Our greedy algorithm wants to choose AK here. Wants to choose this one as the next activity. Now, suppose that there's an optimal solution T star that extends our choices. Okay. So there is an optimal solution that includes all the choices we've made before. So it includes all the choices we've made before, right? So it includes A1, but it does not include AK, which is the solution that our algorithm is proposing. Okay. Then the thing to think about here is that you can actually, without changing the answer to how many activities you can do at most, you can swap the activity the algorithm is proposing with the next activity that exists in the optimal schedule. So again, let's say the optimal schedule is A1, A2, A3, A7. Let's say it's these 4. Let's say that we know this is optimal. Okay. And what we're saying is, well, our algorithm does not want to choose this one. It is not going to choose this one. It's actually going to choose AK. However, because we're choosing the activity with the closest ending time, right, with the smallest ending time, if instead of taking A1, we take AK, right, if we look at AK instead, picking AK will not invalidate any future activities. So A3, A7 will still be valid because AK ends before AI, which was valid before. Therefore, A3 and A4 are valid. And in addition to that, there's nothing that it invalidates here because this part we've already picked. It is the most optimal, we know for sure. And for this part, this might have gone further back and invalidated something else, but it doesn't matter that this became valid, right? It does not change, and the number of activities that we have total is the same. So because of that, you can imagine that you can now consider a new schedule where you swap these activities and take the AK, the one your optimal algorithm would pick. And in that case, now your schedule that you are building up so far is still optimal, right? So your greedy algorithm always picked an optimal solution. Cool. So again, so the algorithm is correct. We never rule out an optimal solution. At the end of the algorithm, we've got some solution, so it must be optimal. Cool. And if you wanted to prove this formally, you would use induction. You would prove it using inductive hypothesis, a base case, inductive step, and the conclusion. And this should make sense to you because basically our inductive hypothesis is that after adding the teeth activity, the teeth thing that we're going to pick, there is an optimal solution that extends the current solutions. So we have not ruled out all optimal solutions. So even after adding teeth, there is still an optimal solution that extends that can keep going using the teeth activity that we just picked, right? And the base case here should be pretty obvious, which is if we have added no activities, then obviously there's an optimal solution that extends the set of activities that we have right now, which is none of them, because there is a solution, right? The solution exists to the problem, right? The inductive step is the part we just did, which we said, hey, I've already added up to I activities. I'm considering the kth activity. And what I'm going to show is that when I add the kth activity, if I added using the definition I picked, then this kth activity, there will be an optimal solution that extends the kth activity. So even if I include the kth activity, there's still an optimal solution that includes the kth activity. And that's what we just did before. Therefore, after adding the last activity, there's an optimal solution that extends the current solution, right? Which is just a convoluted way of saying that the solution we have is optimal. Right. So let's clear that. Let's move on. Yeah, so the greedy works. Now let's look at a few more examples of some greedy solutions. So here this new example is actually called the scheduling problem. So you see this a lot. This is a job scheduling problem. In our case, we're going to talk about scheduling the stuff you have to do. So if you remember, for the activity selection problem, you were given the start and finish times. For the job scheduling problem, you are going to be given a set of jobs that you need to do, aka complete your 285 homework. And for each job, you're going to be given a time, which is how long it takes for the job to be completed. And you're going to be given a cost I, which is the cost you pay per hour for the job to be finished, right? So here's a good example, just to make sure that you understand this problem. We have two activities, doing your homework or sleeping. And doing your homework is going to take you 10 hours, and it's going to cost you 2 units per hour. Okay. Sleeping is going to take you 8 hours, and it's going to cost you 3 units per hour. And here's the key part, until it's done. Okay, so all of these activities, this is the cost you incur until you are finished. Okay, we're back. So apologies for that. I had to jump into a meeting. So let's see if I can cut this. Anyway, for the scheduling problem, you're given n tasks. And task I takes ti hours. And for every hour that passes until task I is done, you have to pay C1. Oh, I am not sharing my screen yet. Hold on a second. Here we go. I am now sharing my screen. Okay, so coming back to this, we are looking at the scheduling problem. You're given n tasks, and each task I takes ti hours. And not only that, but you are also you're also given a cost per hour. So CI is the cost per hour for every task. So that's how much it costs until it is done. So looking at the slide here, you can actually you can consider 2 options. So either you do your homework first and then you sleep, or you first sleep and then you do your homework. And essentially the way you calculate the total cost, if we take a look here, is if you do your homework first and then you sleep, then your cost is going to be 10 times 2, because it takes you 10 hours to do the homework, and each hour you don't do it, it costs you 2. And the cost to sleep, it's going to cost you 3 for each hour you don't sleep, and you end up not sleeping. For each hour you are not done sleeping, and you end up not being done sleeping for 10 plus 8 hours. So that gives you a total cost of 74. And the other way around actually gives you a lower cost. So it is better for you to sleep first and then do your homework, because your homework cost is 2, and that's 10 plus 8 times 2 is 36 plus 3 times 8. So total actually gives you 60. Moving on to the next slide. This problem actually has a little bit of optimal substructure. So something to keep in mind here is that suppose you have an optimal schedule. Let's say A, B, and C, D is like, this is the way to minimize the cost of the jobs is to run job A first, then job B, then job C, then job D. Then this subschedule of job B, C, and D, this must also be optimal. So if you only had the 3 jobs, so if you didn't have job A, the optimal way to run B, C, and D must be B, C, D in that order. And why is that? Well, you should pause the video, think about why this is the case. One way to prove this is try to do it by contradiction. So essentially what happens is, if this was not optimal, then that means there is some other ordering of B, C, and D that is better. But if that ordering is better, then you can do job A and then that ordering, and that will be better. Okay. So this seems amenable to a greedy solution, which basically says, first pick job A, take the best job possible, and then solve the rest of the problem. And by solving the rest of the problem, what we do is we'll take the best job first and then solve the rest of the problem. And then what we do is take the best job first and then solve the rest of the problem. Okay. And once you get to the very last job, then that's an easy problem. That's your base case, right? Because the way to minimize the cost if you only have one job to do is to do it. So here we're going to talk about what we mean by best. We are going to define a couple of new variables, x, y, z, and w, just for succinctness of, because we're only going to be considering 2 activities, and I'm trying to save some space instead of using ti and ti. Okay. So of these 2 jobs, which do we do first? So again, we're going to consider a simpler case where we're only looking at 2 jobs at a time. So the first job is job A, which takes x hours and it costs z units. So again, x hours is the t sub I that we had before, and then z units is going to be the c sub I, right? So this is the units, how much it costs per hour until it's done. And then we have job B, which is going to take y hours to do, and it's going to be how much does it cost for W is going to be how many units does it cost per hour until it's done. Okay. Then if we consider these 2, we consider the total cost of both arrangements for this job. So one way to arrange this is to do A, then B. So the cost of that is going to be x times z, because it takes x hours to do job A and it costs z units per hour, plus x plus y, because it's going to take you couldn't do job B while you were doing A. So it's going to take you x hours plus y hours to finish job B. And for each of those hours you haven't finished job B, you're going to be paying the cost W. So that's A then B. And then similarly for B then A, you can derive a similar formula. And the thing to note is that assuming that it is better to do AB and then BA, then you actually derive this equation here above that just popped up. You actually derive this equation where you have xz plus xy times w. So that's exactly what we had here below for the cost of AB. And then the other side is exactly what we have for the cost of BA. So it's YW plus x plus z, right? So rearranging this, the first thing you do is you can distribute the W out to both terms and distribute the Z out to both terms. And you will be given this YW plus XZ plus YZ, XZ plus XW plus YW plus XZ plus YZ. Then what you notice here is that you can actually cancel like terms. So you have XZ and XZ on both sides. You also have YW and YW on both sides. So they cancel, and the only thing left is XZ and YZ. And that's what you have here. Then dividing, so this W corresponds to job B. That's the cost of job B. And then you have this X, which corresponds to the number of hours that job A takes. So one intuition that you might want is you want to split everything so that on one side you have job B, and on the other side you have job A, because that will help you compare something about job B to something about job A. So here we're just rearranging terms. So what we're doing is we're actually dividing the X on both sides, and then we're also dividing by Y on both sides. So that gives you W over Y on this side, and that gives you Z over X on this side. So here, W over Y, if we notice, that is the units per, the cost of job B, the units per hour until it's done, how much it costs us per hour. And then Y is how much it costs, how long it takes to run job B. So you can actually measure this as the cost of delay divided by the time it takes. So that's this ratio. And then it's the exact same ratio for job A, except now we're only looking at job A. So really what we're saying is that what matters is the ratio. So if the cost of delay divided by the time it takes to do your job is very high, right? So here A is the higher, then that means that you really want to do that job first, okay? And that's actually where the solution for the greedy algorithm comes from. You can already see that you can make a greedy algorithm here. So again, if we take here, the greedy algorithm is basically pick the job with the biggest cost of delay to time it takes ratio. So I'm going to skip this part. We skipped it during lecture, but it's trying to explain why this works. There's some intuition here, which is basically like the job that costs you the most per hour. And then how how long it takes to actually do is the job that you want to do first, because otherwise you're going to be paying that cost per hour for additional hours. Another way to think about this is that if you already have chosen some jobs, so here we've already chosen up to job E. So we've already chosen these jobs. We know this is optimal. We're going to assume this is optimal. And obviously the base case is that this is empty. So by definition, it's optimal. And we're going to consider choosing a new job. So let's say our greedy algorithm says to choose job B, right? Then what we notice is that, say, this is the optimal schedule, job C, job A, job B, job D, okay? Let's say this is some other optimal schedule that we know ahead of time, but our greedy algorithm wants to pick job B. Then essentially what happens is that if you choose the next job, let's say B maximizes the ratio, but it's not the next job, then you can actually switch jobs A and jobs B and nothing else will change. And we just showed that the cost of the solution won't increase. Okay, so you can actually swap, you can do job B first and then job A, right? And these are the two jobs we were considering before. And we showed that because job B is the one that has the biggest cost ratio, right? Then the total cost of job A and job B can only be better by having job B first, right? But we assume our original one was optimal. So you actually can't get better, but what this means is they won't get worse, right? And then you can repeat this with job B and job C. So by the argument that we had before, where like for any two jobs, the one with the highest cost to time ratio is the one you want to do first. If you have some optimal solution where that job is not the one that's first for whatever reason, you can actually swap it with the job right before it, and your cost can only get better, right? And if you repeat that multiple times, then you get to the schedule where the job B is the one that's picked next. Cool. Okay, moving on. Let's clear all drawings. You can actually prove this by induction if you want to try that. That's how you would prove it more formally. There's a full proof in the lecture notes. Cool. So here's the algorithm for scheduling jobs. You're given a set of jobs. You sort jobs in decreasing order by ratio, and then you return jobs. The running time is n log n because you have to sort them. And now you can go, you can optimize your schedule peacefully in the optimal way. So what did we learn? We learned a greedy algorithm that works for scheduling. This followed the same outline as the previous example, which is first identify some optimal substructure, and then find a way to make choices that won't rule out an optimal solution. So our last example for today, which we actually didn't finish during lecture, but this is for Huffman coding. Here's an everyday English sentence in ASCII. So ASCII, again, if you guys remember, is where every character corresponds to 8 bits. Here's another English sentence, not an English sentence, just a random set of characters. And here's what the ASCII looks like. So one thing to notice is that the letter E appears very often in English, but we still use 8 bits to encode it. So in a sense, ASCII is not a very efficient way to encode English because we use the same number of bits for every letter. And here we can actually look at the actual distribution of the letters in the English language. So E occurs the most often, followed by T, and that's because THE, the, is a very common English word. For simplicity, we're going to go with this example where we have these are the percentages, percent occurrence of particular letters in our language. So in our case, A occurs 45% of the time. So the intuition is that you want to use less bits to represent A because that's going to be more efficient because it occurs more often. Okay, so how to encode them as efficiently as possible. So one option is you can use ASCII. So that means because we only have 6 letters, then we have to use 3 bits, which means we can encode up to 8 letters, and we give each letter a unique value. So 000 for A, 001 for B, 010 for C, 011 for D, 100 for E, and 101 for F. But this is wasteful. First of all, 110 and 111 are never used because, that's information that we never use. And in general, we probably want to represent A in a shorter way because we're going to see it a lot. So instead of having 3 bits, we're probably going to use fewer bits. Okay. So our other attempt might be, hey, okay, let's just use the fewest bits to represent the letter with the highest frequency. So you could say, okay, letter A, which is here occurs 45% of the time, you're going to be bit 0. Letter B, you're going to be bit 1. Then letter B, which occurs the next most often, is going to be 0, 0. And then letter C is going to be 0, 1. Letter E is going to be 1, 0. And letter F is going to be 1, 1. So this is much better because you're only using 2 bits now at most to represent letters. And for letter A and D, you're actually only using 1 bit. Okay. The problem is that now you can't distinguish between different encodings. So if you have the encoding 0, 0, 0, this could be AAA, or it could be B followed by A, or it could be A followed by B. So now you don't know which of these it is. So this is not a good encoding. It is very space efficient, but it is not a good encoding because you run into overlaps or you can't distinguish which letter you're actually looking at. So what you want to do is you actually want to encode it in a way where none of the letters share a prefix string. So every letter is assigned a binary string. More frequent letters get shorter strings, but no encoded string is a prefix of another string. So here's an example of that. So we can say, look, letter A is going to be 0, 1. Letter D is going to be 0, 0. So again, they don't share. So if you see a 0, 1, you know it's A. And what you'll notice is that no other letter starts with a 0, 1, and no other letter starts with a 0, 0, right? So for B, we have to give it 1, 0, 1. For C, we give it 1, 1, 0. And what you'll notice is no other letter starts with 1, 0, 1 or with 1, 1, 0. So letter F gets 1, 0, 0, and letter E gets 1, 1. So again, this is a little bit less efficient, but now you can immediately decode a string by just running through it. So you can say, well, 1, do I have any numbers that start with 1? I do. B, C, and E might be it. 1, 0, 0. So that's letter F unambiguously. Okay. And then 1, 0, 1 is letter B unambiguously. There's no other possibility for this because 1, 0 is not, it does not exist. And then 0, 1 is letter A. So this is FBA. Cool. And then the question that we want to answer is, what is the most efficient way to do a prefix-free coding? That is, how can we use as few bits as possible? So, and this is not the way to use the fewest bits. It turns out that a prefix-free code, well, actually, we ended lecture originally here, so we'll just cover this on Monday, and that is the end of the recording.